Okay, I got cut off because I ramble. Sorry. Hopefully in some of these cases you're putting me on that like fast forward setting. Okay, so taking a look here. I'm gonna hit this hard again, and I'm also going to again, you should have watched Professor Dave. But force and direction of motion matter when defining work, and this is relevant to what we've talked about, what I kind of referenced in the last one, but I will go through it more in depth. Okay, there's no work done if there's no displacement. So, like Professor Dave said, when you're pushing a brick wall, you can push and push and push, and you can be exhausted, but there's no formal like displacement, so there's no work done. Okay. Forces can be positive, negative, and zero. And I really liked his like that's part of the reason why I like using other people to explain because they have really nice animations and I just do a lot of hand waving. Okay. Um, so normal force of gravity do no work since they are perpendicular. They cancel each other out. So normal force, if you recall, is the upward force applied to an object that keeps it on the table, and gravity is what's pulling it down. And as long as this thing, my book, is not moving, it is in static equilibrium, which is staying like its basic equilibrium. Now, a person pushing on a box does positive work because the direction they're pushing on the box is the same direction the box is moving. Okay? So friction does negative work. So if you're pushing something, so you're moving and there's a rug, a really thick plush rug on the floor, and you're trying to push a desk across the floor or some sort of object across the floor, that's going to have a greater negative than if you were just sliding across like ice of a pond, or just a tile floor. It's easier to move an object. Okay, so the first question it asks, and this also comes straight from that worksheet, a man holds a 50-kilogram box, arm's length, for 2 hours. There's a duration of time. There is no displacement. So the equation would be, so if you're going to use the displacement equation, you have um, work is equal to force times displacement, right? Woo, that was terrible writing. Okay, which means work equals, so give you a mass, you're there's no real force. I mean, the force applied is, I guess, the normal force. So here, if I draw for you a diagram, there's a normal force of 500 newtons going up. I'm using 10, not 9.8, and 500 newtons of gravity pushing down. But that's an equilibrium. So there's no real force or displacement, so it's zero. Okay? The man holds a 50-kilogram box at arm's length for 2 hours and he walks 1 kilometer forward. How much work does he do on the box? Um, so now you are pushing a box. You're pushing that box 1 kilometer in this direction. So you have the um, up, down, I don't know why it's wigging out on me, 500 newtons, 500 newtons, but your actual force is this way. You're walking this direction. Um, okay, for 1 kilometer. So your displacement is 1 kilometer. And your force, I'm assuming length for 2 hours as he walks 1 kilometer forward. I'm assuming you're applying just 500 newtons of force to oppose it. So 500 joules. I think. The caveat there might be the metric component. So I'll have to look into that. Okay. Okay, 2 meter. Oh no, this is going to be off because it's in kilometers, and joules is Newton meters. So kilometers is 1,000 meters. Sorry about that. 1,000 meters times 500 newtons. So shown work is equal to 1,500 newtons times 1,000 meters. Wow, my pen's really not cooperating right now. Okay, so next one, a man lifts a 50-kilogram box. Okay, again, you're opposing gravity, so I assume you're not accelerating, you're just moving at a constant rate. So a lot of kind of caveats here. 500 newtons up and 2 meters times 2 meters. How much work does he do on the box? Okay, so work and energy. Work changes mechanical energy. If an applied force is positive work, it increases the mechanical energy, all right? So that means if I'm pushing on the box, I'm increasing the kinetic energy, the moving energy, because it should move faster the harder I push. Okay, now if somebody else is pushing on the box the opposite way, it's trying to slow it down, so decrease the kinetic or mechanical energy. The two forms are called potential and kinetic, which you should already know. Potential is the non-moving. This is stored, and this is moving. Okay, so 9 meters above the ground. How much work? So 70 kilograms. You have to oppose gravity, so 700 newtons of force. How much work does Jane do when she lifts Tarzan times 9 meters? How much work does gravity do when Jane lifts Tarzan? That's going to be the 700 newtons times negative 9 meters. Okay. Okay. I need to review this particular sample problem. So I want to skip ahead and go over this. Okay. This is when things matter. Here's my wagon. Here's the angle. Kids singing in wagon. Dad pulling wagon, right? This gets into the roller coaster problem. Holding on. Okay. Notice there, the wagon is going to move this direction. Okay. But the dad is actually applying a force. So the displacement is from here to whatever distance horizontally across the ground in this direction. That's displacement. Now the force, displacement, the force being pulled on, the dad pulling the wagon, is actually in this direction. Okay? So there's actually an angle situation here because this is different than the displacement direction. Okay? The only force that really can matter is the force, the horizontal component of that force. So I taught my freshman, that this breaks into a vertical component and a horizontal component. All right. So that you can kind of split this up and not have to deal with angles. And that's what we do freshman wise. But this is the only force that actually affects the movement of the cart. Okay? So that's why when you're looking at the roller coaster, when the roller coaster, no matter what angle you're traveling, its displacement is this direction, and the force of the chain is also this direction. And because they're parallel, the angle doesn't matter. Okay? Again, it doesn't matter the angle because the chain is pulling and the movement of the cart is on that same plane. Okay? I'm going to cut it there. We'll go over this again and I'll review that other question. But I really wanted to explain this because it's important that you understand this idea. Yeah. So understanding that angle component. So that's even if you're lifting something straight up from the ground, the force you're applying is straight up and the displacement is straight up. But if you pull on something at an angle to drag it across the ground, then the only force that really affects that movement across the ground is this horizontal component, regardless of the fact that you're like pulling it this direction. Okay. Review that a couple times. If you're still struggling with that idea or that concept, let's talk about it. And I promise I'll go back to the other sample play question, but I haven't really talked about the coefficient of friction before. So I need to review that. All right. Have a good day.